So we've extensively talked about tangent lines, but what we haven't talked about is a tangent plane. Now that we're in three-dimensional space, it makes sense for us to talk about tangent planes. Let's first review two-dimensional space or single variable calculus, and in these first two diagrams, recall that if you have a function that's differentiable at some point A, then you can compute the tangent line. But if your function is not differentiable, no tangent line exists because actually as you approach this point, you have two different tangent lines, not one. Well, we'll expand that to three-dimensional space. If you look at a surface and you're looking at some point on your surface, it's possible, if your function is differentiable, to find a tangent plane at that point on the surface. If it's not differentiable, then you cannot find a tangent plane at that point. So what we'd like to do now is to come up with the equation for a tangent plane at any point on a differentiable surface. So first of all, there's two ways that we can describe our surface. We can describe our surface explicitly as z equal to some function of x and y, or implicitly as a function of xyz equal to 0. So if I were looking at the implicit form, then on this diagram, and we can look up at this diagram here, this z could also be defined as f. Now let's suppose that we have some curve that passes through this point AB on the surface. So we just have some random curve that I'll call R. We're going to define the tangent plane by first looking at the definition of our explicit form. Notice that R is a function of x, y, z, where x, y, and z are a function of t. So we're writing R in vector form with the parameter t. In my implicit form, that then becomes f of x of t, y of t, and z of t, which is equal to 0. Now imagine taking the derivative of this equation on both sides. So why don't we do that off to the side here? It might be easier to see the derivative if we draw ourselves a tree. So f is a function of x, y, and z. X, y, and z are functions of t. So if I were to take the derivative of my function with respect to t, then following along my branches, I have the partial derivative of f with respect to x times the derivative of x with respect to t, plus partial derivative of f with respect to y times dy dt, plus partial with respect to z times dz dt. Looking at this derivative, I can see that I can decompose it into the dot product of two vectors, where one vector is the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, dotted with dx dt, dy dt, dz dt. Now remember, this is equal to 0. So this first vector here is simply our gradient vector. And this second vector is the derivative of our curve R. And these are dotted where the dot product is equal to 0. So what that means is these two vectors are or orthogonal to each other. So if we go back to this upper diagram, I can see that I would have a gradient vector and a tangent vector to the curve where these guys are normal or perpendicular or orthogonal to each other. Remember the general equation for a plane from 14.1 requires that you have a point and you have a normal vector. So it turns out that this gradient vector is our normal vector. And this would be the equation of the tangent plane in vector form. It's the gradient vector dotted with the derivative of a curve. So again, this gradient vector, this would be our normal vector. And then this would be our tangent vector. Now it's not a unit tangent vector, so just lowercase t. We'll look at these properties. So our tangent vector is orthogonal to the gradient vector for any point on our curve. And we've just seen that, we've just proven that. And then if you have any point on our surface, all curves passing through the point with tangent vectors having tails at the point are all orthogonal to the gradient vector. Now let's go down to this bottom diagram. So this is what it means. If you look at this second diagram, we have this normal vector and we have our point. And we have a bunch of curves that are passing through this point on the surface. We'll notice that any tangent vector with a tail at that point is going to be orthogonal to that gradient vector. And then we've already discussed that the equation of our tangent plane would be the dot product of the gradient. And this would be for any point A, B, C. And that's set equal to 0. So we'll go ahead and compute that dot product in just a little bit. But for now, we're looking at the equation of the tangent plane in vector form. So what you can imagine is you have this gradient normal vector to our surface. And if you look at all these tangent vectors that are normal to this gradient vector, and you sweep all these tangent vectors around, what you get is you get your whole plane. In this box here is our equation of a tangent plane. And again, we're just looking at the implicit formula. So if you have a point, you have a gradient vector, as long as the gradient vector is not equal to 0, then at the bottom of this box would be the equation of your tangent plane. Partial derivative of x, partial derivative of y, partial derivative of z. So this is the same form of the equation of a plane that we had previously. Example 1, we're given some ellipsoid, so there's some egg floating in space. And we want to find the equation of the tangent plane at the point 2, 0, square root of 5 over 3. Part B says at what point or points is the tangent plane horizontal on this ellipsoid. So let's first look at A. The first thing we need is we need to know what the gradient is. So the gradient is the partial derivative with respect to x, which would be 2x over 9. Partial with respect to y, 2y over 16, so that would be y over 8 if I reduce. And the partial with respect to z would be 2z. Once I have that gradient vector, I'm going to evaluate this vector at my given point. So this would be my A, my B, and my C. If I evaluate this gradient vector at the point 2, 0, square root of 5 over 3, that gives me the vector 4 over 9, 0, 2 times the square root of 5 over 3. So this gradient vector is normal to my tangent plane at the point 2, 0, square root of 5 over 3. Now all I have to do is plug this into the equation for my tangent plane. Remember, this is the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, which gives me the equation 4 over 9 times x minus a, which is 2, plus, since the second coordinate is 0, that middle term goes away with the partial with respect to y, and I just have my z, which would be 2 times the square root of 5 over 3 z minus my c value, which is square root of 5 over 3. Set this equal to 0. So typically we wouldn't leave the equation in this form. We would get rid of the parentheses. So 4, 9, x minus 8 over 9 plus 2 square root of 5 over 3z minus, this becomes 10 over 9. Set that equal to 0. Keep all the variables on one side. 4 over 9x plus 2 square root of 5 over 3z equal to positive 2. So here we have the equation of the plane that's tangent to our surface, our ellipsoid, at the point 2, 0, square root of 5 over 3. If we look at part B, we're asking to find the point, if there is a point, where the tangent plane is horizontal. So let's just think about that for a little bit. And I'm not going to draw the ellipsoid. What I'm going to do is I'm going to just sketch a horizontal tangent plane, okay, given any surface. It's not a particular surface. So if we look at a horizontal tangent plane, notice that at some point C, which is a z value, we're going to have a normal vector. So that normal vector, I'll call this n, is going to be 0, 0, some c value. Now, if my ellipsoid has a horizontal tangent plane, what that means is the normal vector or my gradient vector for my ellipsoid would need to be parallel to this vector. So I don't know where my ellipsoid is. I could find out easily by graphing this, but I know that my gradient vector, wherever it may be, would need to be parallel to this normal vector. So that's all I have to do is I'm going to look at my gradient vector and I'm going to set it equal to 0, 0, c and solve. So my gradient vector was 2 times x over 9, y over 8, and 2z. Set that equal to 0, 0, c. And the equation 2x over 9 equal to 0 means x is 0. Y over 8 equal to 0 will give me y equal to 0. And then I have 2z equal to c. So here x is 0, y is 0. Unfortunately, I can't solve this last equation, which sometimes happens. So I really can't find the vector at this point. However, notice I know that the x and the y values have to be 0. So I'm just going to plug these values into my function, my ellipsoid. And once I plug these values into my function, what remains would be the z value, where there's a horizontal tangent plane. So if I put in x is equal to 0, y is equal to 0 into my ellipsoid, I get z squared minus 1 is equal to 0. Solving, I get z is equal to plus or minus 1. So when x is 0, y is 0, z is negative 1, x is 0, y is 0, z is positive 1, these are the points where we're going to have horizontal tangent planes. And you can check by graphing this ellipsoid in graphing programs such as Desmos, or if you have a 3D grapher, and you'll see that we have this ellipsoid with a center. Ooh, interesting. I'm going to try to graph. So we have this ellipsoid here, and the center should be at the origin. If you look at above and below, this looks like it's at 1 and negative 1. This is where we can see that there's probably going to be horizontal planes, right, passing through. So that makes sense because the shape is an ellipsoid. Let's look at another example. Example 2, we have this surface, x equal to z minus tangent inverse of yz. And we want to find the tangent plane at the point pi 1, 1. So this would be our A, our B, our C. I do have an issue. Notice that my equation is not in implicit form, it's in explicit form. Well, not quite explicit because it's not solved for z, but I do have to get it in the correct form so I can determine my partial with respect to x, y, and z. If I go ahead and set this equal to 0, I get x plus tangent inverse of yz minus z equal to 0. So now that I have it in implicit form, I can go ahead and correctly identify my gradient vector. My partial with respect to x is 1. Partial with respect to y would be the derivative of tangent inverse. So that's going to be 1 over 1 plus the argument yz squared. And then I would have to multiply it by the derivative of the argument with respect to y, which would be z. The partial derivative with respect to z would be looking at the two terms, the tangent inverse and the minus z term. So for the tangent inverse term, it's going to be 1 over 1 plus the argument yz squared times the derivative of the argument with respect to z, which would be a y. And then we also have that minus z, so the partial derivative there is just minus 1. So here's my gradient vector. I'm not going to bother to clean it up because remember I have to evaluate this gradient vector at a specific point at pi 1, 1. Now if all I was doing was finding the gradient vector, then I would probably clean that up. This would be 1, 1/2, negative 1/2. I have my gradient vector, I have my point pi 1, 1. The equation of my tangent line will be x minus pi plus 1/2 y minus 1 minus 1/2 z minus 1 equal to 0. Again, I could stop there or clean this up by getting rid of the parentheses, combining like terms, throwing the constant onto the right-hand side. I always put a line through my z's because my 2's and my z's look the same. All right, so it looks like this is going to be x plus 1/2 y minus 1/2 z equal to pi. Let's now look at this next box and look at the equation for a tangent plane if the equation is explicitly solved for our z value. Notice that the equation for the tangent plane is going to be z equal to partial of f x minus a partial of y minus b plus partial or plus f of ab. Let's go ahead and see where this comes from. Let's go ahead and look at this explicit form. And maybe I'll do this above here. I have some space. Notice that if z is equal to f of xy, and I set this equal to 0, I have z minus f of xy is equal to 0. So we're going to compare that to the implicit form with the equation set equal to 0. My point A, B, C is going to be the point A, B, but now C is our z value, which would be f of a comma b. So this is the point that we're going to use. We need our gradient vector. Oops, that actually should be over the f. When I compute the gradient vector, I'm computing the gradient vector with z minus f of xy. Remember that gradient vector is equal to the partial derivative with respect to x. So z has no variable x. So we're just looking at the partial derivative of this negative function with respect to x. We're evaluating it at this point AB. Partial with respect to y would be negative function partial with respect to y evaluated at the point AB. And then when we take the partial derivative with respect to z, it's just 1 because our function f of xy does not have a z value in it. So this is our gradient vector, and we have our point AB, f of AB. So now when we put that into our implicit formula for the equation of a tangent line, we get negative partial with respect to x evaluated at our point AB, x minus a, minus the partial with respect to y evaluated at AB times y minus b, plus, this is a 1, so it's 1 times z minus c, but c is the point f of AB. And then we set that equal to 0. So we're just using the equation for the implicit form of the equation of a tangent line. Now notice if I were to get rid of this last set of parentheses and solve this equation for the z value, I get the equation for a tangent plane in explicit form. So it's always nice to know where these formulas come from. In example 3, we have to find the equation of a tangent typo plane at the point 1, 1, natural log 2. Our surface is z equal to natural log of x squared y plus 1. So our surface is written in explicit form. I can use the above equation for the tangent plane. I need the partial derivative with respect to x. That should be 1 over, because it's natural log, the argument x squared y plus 1 times the derivative with respect to x of the argument. So that looks like 2xy. And the partial with respect to y, I'm not even going to bother to write this in vector form because notice in my equation of the tangent plane, I don't really need the vector, the gradient vector. So the partial with respect to y of this function would be 1 over x squared y plus 1 times the partial with respect to y, which would be x squared. Now I'm supposed to be evaluating this partial derivative with respect to x at the a is equal to 1, b is equal to 1. Notice I don't really care about the c value. When I evaluate the partial derivative with respect to x at the point 1, 1, it's equal to 1. Evaluating the partial with respect to y at the point 1, 1, that would be equal to 1/2. And I'm done. My equation is z equal to x minus 1 plus 1/2 y minus 1 plus my f of a b, which would be this natural log of 2. Maybe I can get rid of parentheses and clean this up to get z equal to x plus 1/2 y minus 3/2 plus natural log of 2. And I believe that's the best I can do. The next concept we're going to talk about is our linear and approximations. So recall from Calculus 1 that if you have a curve, and maybe this curve is difficult to evaluate at some point, so instead what we might want to do is drop ourselves at some nice point A, a tangent line. And the tangent line is easy to work with, so if I wanted to find some value for my function at some point near A, it's going to be approximately equal to that same y value on my tangent line. So you can expand this idea to tangent planes. The idea is that at any point AB, f of AB, we can approximate values from our surface by using values on our tangent plane. So we can find values close to this AB, f of AB. By looking at those values on the tangent plane, they're going to be approximately equal to corresponding points on our surface Z. So our linear approximation, and we're still calling it a linear approximation because we don't want to call it a planar approximation. It's still going to be using a tangent plane. So a linear approximation using tangent planes would be given by this L of xy. So it's a partial derivative with respect to x, x minus a, y, y minus b, and the f of a, b. It's just the explicit form of a tangent plane from our previous concept. In example 4, we're asked to find the linear approximation for the given function at the given point. And then we're going to use this linear approximation to estimate the value of the function at the point 1.2.9. So the point 113, that is a point on our function. Oops. So this is on our function f. And that's what we're going to use for us to create our linear approximation. This would be my A, my B, and my C. The first thing I need is to figure out the partial derivative with respect to x and y and evaluate it at the A value of 1 and the B value of 1. I prefer to use f of xy equal to 9. I don't want to use quotient rule. 9 times x squared plus 2y to the negative 1. I prefer to use chain rule. When I compute the partial derivative with respect to x, it's going to be negative 9x squared plus 2y to the negative 2 times partial derivative with respect to x of the inside would be 2x. And I'm not going to simplify it because my only purpose is to evaluate this at the point 1, 1, which would give me negative 9 times 3 to the negative 2 times 2. So it looks like that's going to be negative 2. The partial derivative with respect to y is negative 9 x squared plus 2y to the negative 2 times the derivative with respect to y, which would be 2. And if I evaluate this partial derivative at the point 1, 1, looks like it's negative 2 as well. Okay. So now my linear approximation with respect to x and y will be negative 2, x minus 1, negative 2, y minus 1, plus my c value of 3. I can now use this linear approximation to approximate the value of my function at the point 1.2 and 0.9. Now I didn't bother to get rid of the parentheses, combine like terms, and so on in the linear approximation. In fact, you don't want to do that. If you're using your linear approximation to evaluate some points, it's always easiest to keep it with the parentheses, because now notice when I put in 1.2 for x and 0.9 for y, it's much easier for me to figure this value out without even using a calculator, because this is simply negative 2. 1.2 minus 1 is 0.2, minus 2 times 0.9 minus 1 is negative 0.1, plus 3. And I can do that without a calculator to get negative 0.4 plus 0.2 plus 3. And that would be 2.8. Without even using a calculator, I can use my linear approximation to say f of 1.2 comma 0.9 is approximately equal to 2.8. So we also use linear approximations to define our differentials, which is our next topic here. It's easiest to understand differentials when we look at the diagrams. Let's go back to our two-dimensional space. Well, see, we have this curve and we have a tangent line. Let's look at the point x. This point x corresponds to some point P. This point P is on the curve and it's also on the tangent line. Remember, the tangent line is just your linear approximation. If we go some distance, delta x, then we're going from x to x plus delta x. That point corresponds to this point Q on our curve. So the change in our y values which would be the change in our y values from x to x plus delta x, is delta y. However, this point x plus delta x also corresponds to a point on our linear approximation. So when we look at the change in the y values for our linear approximation, that would be dy. That's our differential. So the differentials are the change on our linear approximation or our tangent line. Take this idea and look at this in three-dimensional space. Let's say that we have some point AB, and we go some delta x and some delta y to get to this new point, xy. At AB, this point corresponds to a point that is on the surface and also on the tangent plane. When we're at the point xy, we've gone a distance of delta x and delta y. This point now corresponds to a point on the tangent plane. And here we're looking at a change in our z values. So since it's on the tangent plane, it's our differential dz. But it also corresponds to a change in the z values on our surface, which is our delta z. So when we look at our differential dz, it's going to be approximately equal to the change in our z value. Looking at this box, we can see that this dz, the differential, approximately equal to delta z, which is the change on our surface. That's going to be equal to the partial with respect to x at AB times dx, partial derivative of y at AB times dy. In example 5, we have a volume, which is equal to pi r squared h over 3 of a right cylinder cone. It has a change in the radius from 6.5 centimeters to 6.6. So the change in the radius would be your dr. And it has a change in height from 4.2 to 4.15 centimeters. That would be our dh. We're supposed to approximate the change in the volume. So we're supposed to figure out what the change in the volume is. But we know that it's approximately equal to the differential of the volume. And that would be equal to the partial derivative of the volume with respect to x. So you can look at your x value as being r for radius. So the partial with respect to r, dr, plus the partial derivative with respect to the height times dh. Our dr goes from 6.5 to 6.6. So dr is a positive 0.1. dh is going from 4.2 to 4.15. So that's a negative change of 0.05, right? Because you have to go from your starting to your ending, from your starting to your ending point. Now all I have to do is plug those values in. The partial derivative of the volume with respect to r, well, if you look at your volume equation, it's going to be, with respect to r, it's going to be 2 pi r h over 3. And then we're going to multiply that by 0.1. The partial with respect to the height is going to be pi r squared over 3. And we'll multiply that by the negative 0.05. The values that we're putting in, these A and B values, remember that's our starting. So my starting radius was 6.5. That's like my A value. My starting height was 4.2. That would be my B value. This now becomes 2, I'll write this as 2/3 pi. My R is 6.5. My H was 4.2. And then timesing that by 0.1 plus pi over 3. The starting R is 6.5. I square that and then multiply it by negative 0.05. Oops. So at this point, I would just plug all this into a calculator, and it's approximately, why don't I go 2 decimal places? I'm not using significant figures, 3.51 centimeters, but this is a change in volume, so it's cubic centimeters. Example 6 is our last example, and it's similar to example 5, where we're going to approximate a change. So here we're going to approximate the change in our z value. So the change in the z value, we're going to approximate delta z when the independent variables change from negative 1, 1. So that's our starting AB to negative 0.97, 0.98. And then we're also going to compute error. So there is a difference between relative error and error. Error is just the absolute value of the difference. Relative error is our percent error. We're given our function z, which is 3xy plus x squared minus y squared. And our delta z, our change in z, is approximately equal to, dz, sorry, not dx, dz. Remember that's equal to the partial derivative with respect to x, evaluated at our point AB, which is negative 1, 1, times the change in x, plus partial derivative with respect to y at negative 1, 1, times the change in our y value. So if I compute the partial derivative with respect to x, it's 3y plus 2x. And then evaluating this at negative 1, 1, looks like it's positive 1. The partial derivative with respect to y is 3x minus 2y. Evaluating at the point negative 1, 1 gives me a negative 5, which means the change in z is approximately equal to 1 times negative 0.03. So negative 0.03 minus 5 times 0.02. And that would be equal to a negative 0.13. So the next thing we need to do, we found the approximation. The next thing we need to do is figure out our relative error. So remember, when you figure out error, it's just going to be your actual minus your approximation in absolute value. So our actual is our delta z. We're going to subtract our approximation, which would be dz. But it's relative error, it's a percent error. So we divide by the actual, which is our delta z. And then we're going to multiply it by 100 because it's going to be a percent error. I have to compute the actual. So the change in my z values is going to be my starting value minus my ending value. This definitely needs a calculator. This would be -3 plus 1 minus 1 minus, I think I'm going to need a bracket here, 3. So all I'm doing is substituting this value into my function, my z function, times -0.97 times 0.98 plus -0.97 squared minus 0.98 squared. I'm going to plug that into my calculator, and I believe it's -0.1287. Oops. So double check me on that. So when we look at our relative error, it's the absolute value of -0.1287 minus a negative, so plus 0.13, divided by the actual, which is the -0.1287. And you don't need to have it negative, it could be positive. So as a percent, right, because you're timesing it by 100, it's approximately, it turns out to be 0.01010101, so it's approximately a 1% relative error. At the very bottom here, we have a function of 3 independent variables, x, y, z. And we can also find our linear approximation. It wouldn't be a tangent plane. It would be a tangent surface, some three-dimensional surface. It's hard for us to visualize, but again, we can still do the math where the change in our function w is going to be the partial with respect to x dx plus partial with respect to y dy plus partial with respect to z dz. And expanding further, we can go into 4 variables, 5 variables, 6 variables, and so on. So any n amount of variables, we can still figure out this linear approximation. So that's it for this section.